Dude, Kevin, when'd you get a mohawk? You look sick. Kevin with the mohawk?
What? I just realized that when you use OBS, Discord like tries to hide user usernames with like the dot dot dot. But if you right click over, you can see like their full thing over here, which makes no sense. But that's on Discord's part, not mine. Time now is 9 p.m. Alright. Let's do this thing, I guess. I am streaming this screen. Yes. Yes. Okay. So, I guess we begin. Oh. Right. So, once again, preamble. It's not meant to be like a 100% you can guarantee pass if you like listen to me kind of deal, but it's called a speed run because it's generally what you need to know for the exam. I've got the list of topics right here, the same one I posted previously. I'll be going through the ideas first. I might do tutorial questions later if I feel up to it. We'll see. So here we go. Let's do this. Dependent and independent events. What does it mean for events to be independent? Mathematically, there is only one way, okay, technically three ways, but there's only one main way to check if two events are independent. And that is with this formula. If the events are A and B, we've got A intersect B. And if and only if they are independent, this will be true. This is like the main one to follow. You may have also seen another formula going around. I think this is like the base theorem one, where you've got this. This formula also exists. If you try to sub this into here, you get two different formulas that still mean the exact same thing. You can also use those to check for independence. It will be, if you sub this in here, they've got PB, it should be this. I will double check. Where are the slides? Maybe it's not this one, it is this one. First of all, I didn't start the timer. Then we will look up independent. There we go. So let me just double check that it's the right thing. P intersect B, PA times PB. That is what I've written over here. Top one. A given B is PA. That's what I have over here. B given A, that's what I have over here. So for two events to be independent, it just means that when you have probability of A, probability of B, and you have A intersect B, the values on both of these equal signs, this one and this one, should be the same. The independence formulas, that's what I've just said. In words, what does it mean for something to be independent? That is this specific sentence. I don't think there's any like paraphrasing or any different way you could mention it. It is exactly word for word this. I'm pretty sure she won't test like, what does independence mean in words? But just so that you know what it is when you're using it in numbers and stuff, independence means that the information that B occurs doesn't affect the probability that A occurs. A doesn't care if B occurred. The probability of A will still remain the probability of A. That's what this means here. Because A given B means, if you have something given something else, that just means that this... Oh wait, I have a laser pointer, right? I think. Laser pointer? No? Oh, I do, yeah. The fact that B occurs has absolutely no bearing on whether A occurs. The probability of A occurring, if B occurred, is still the same as the probability of A. That's what this sentence means. It's not about disjoint, it's not about having no influence. It's just saying that if B occurs, A doesn't really care. Probability of A will still be the probability of A. Same with B. If A were to occur, B doesn't care. Probability of B would still be the probability of B. So far, I guess I should have done this earlier. Does my audio sound good? Are you guys able to hear me? I'm gonna assume.
Yeah.
Alright, cool. Thank you, person. I can't check my Discord right now because I have that minimized. Alright, next up, conditional probability. Let me erase this. I have these L1, L2 numbers here. These are the lecture notes. So if you want conditional probability, you look at lecture 1 and lecture 2. I like that sound, but not right now. Conditional probability. What we have is our classic formula. This one. No, I don't want it as laser pointer. I want it as a pencil. Probability, no? Okay.
Hey, he never come back already. You got no slot for him already.
Probability of A intersect. 1 second. Alright, there's Twitch as well. I didn't check my Twitch chat. Thank you, people.
Oh.
Is that a bot? Wait, hold on.
Again.
Okay, audio is good on Twitch. Alright, sick. Yeah, if Discord has a limit on the number of people, I'm sorry, but that's what the Twitch stream is for. So if your friends are unable to come in, that's what Twitch is for. So you guys can look there. I will periodically look at Twitch. I hope I remember it. Yeah. Alright. Now, conditional probability. We've got, where's my cursor? We've got our famous formula here. This one shows up all the time. I'm not even sure this is exactly Bayes' theorem, because Bayes' theorem, when you Google image it, it looks like a bunch of different things. But I'm just gonna call it the formula. I don't know what it's called. I just know it's important. This is the formula for conditional probability. What it means to have a conditional probability means that you are given a piece of information. Let's say it's the fact that the event B has happened. So you're given this. You know this information. Right? Info. And because you know this information, you're able to rule out certain possibilities. That's why for the most part, probability of that's why for the most part, if A and B are not independent, the probability of A given B isn't the same as just the plain old probability of A. Because what you are doing here, I'll just draw the Venn diagram real quick. So we've got, select this. We've got our Venn diagram. We've got our two events. Here's the sample space omega. Here's event A, and here is event B. Now, here we have A given B. A given B means that we already know that B happens. What that means in the Venn diagram is that instead of considering everything in omega, we don't do that because we know that B has already happened. So this current thing we're examining is guaranteed to be inside B. So if you have something given B, this means that only inside B are all the possibilities you're considering. And now, if you're trying to find the probability of A, given that B happened, then you will know that the probability of A will only be this portion right here, because that is the only part of A that is in this red shaded region that you have guaranteed, that you have not ruled out as a possible outcome. That is why P of A given B is this red region over the whole probability of B stuff. This is what that formula means. Probability of B, that is the red region. Probability of A intersect B, that's this part right here. And that is what A given B means. I'm going to double check in the slides in case I missed anything. Conditional probability. Yep, independence. Multiplication. This is the same formula we've always encountered. This thing I discovered yesterday, I guess rediscovered. I don't think this is coming out. There's 3 variables in it. Then there's like B given A, C given A intersect B. I don't think this is coming out. I don't think we need to concern ourselves with that. Conditional probability. What else do we have? Partitions I'll talk about right now actually. So we've done conditional probability. We've talked about what it means to have a conditional probability and its formula. So now we're going to head on to Bayes' theorem, which means I get to advance the timer. So sick. Bayes' theorem. Now we will go to our thing. Let me clear the workings. Bring my pen back. Okay, Bayes' theorem. Bayes' theorem is this weird thing because let me open up a new window, and I will show you what I mean by the searches not making sense. Where is my window? Okay. So if you just Google search Bayes' theorem and just look at the chat. This tends to be what you find. It's transparent. You get this thing. A given B equals to B given A. Maybe I can A given B is B given A times P of A over P of B. I personally don't like this because there's a bunch of variables over here. I much prefer the almighty formula I've mentioned previously, where we've got probability of A given B is probability, it's not an equal sign, probability of A intersect B over the probability of B. I like this formula because it's less things. You've got one thing over here, you've got one thing over here, and you've got one thing over here. Compared to this formula is like 1, 2, 3, 4 things. Plus, with the visualization I mentioned earlier, you can get this formula back. If you draw the Venn diagram and you think about what it means to have A given B, you will arrive at this formula. I don't know if this formula is specifically called Bayes' theorem, but it shows up so much it might as well be. That's what I meant by Google images, because I don't know, man. I don't actually know what Bayes' theorem is. I just know that it shows up when you do this, but this one is just so much better. Okay, next up is partitions. So if we go to, actually no, I'll just explain what partitions are myself. So let's say we've got let's say we have 2 events, A and B. We'll draw them out. So we've got our sample space, A and, maybe that's a bit too small. A and B. This is our sample space. This is kind of how it's looking like right now. You can redraw this in a different format that can, I don't know, help with different things. So taking this scenario and redrawing it in a certain way will give us this. We've got our sample space, as always, but we split apart the sample space into B and B complement. No, that's not complement. B complement. Because here, in our original diagram, there's some probability of B happening and some other probability where B doesn't really happen. That's what we've got down here. And A would be something like this. Because there's some probability that that A happened with B and some probability that it didn't. Note that B is not a circle anymore. It's now 2 halves of the sample space. This is what a partition is. Partition. To partition an event is just to split it apart into different events. I think one of the best diagrams is, yeah, this is the diagram I drew. You take one event and you split it up. This will give you a formula that will be, let's say you wanted to find the probability of A, but you only know A happening with B and A happening with not B. That's still okay, because this probability of A, we've got 2 halves. We've got the half here and we've got the half here. So let's do it for the first half. First half is A intersect B, because we've got this part in A and that is inside this B half of the sample space. Likewise, we've got A intersect not B, B complement, because you've got this half of A inside the B complement part of the sample space. Now, using our almighty formula up above, we can realize that we can sub it in, and what we'll get is P A intersect B, P B. You can verify for yourself that this is just the same formula as the one we've had above. And we apply it to the one on the right as well. We've got A intersect B complement, B complement. This is what it means to have the partition of A, or like to find A through its partitions. Because A has been split apart into like this left half, this left half, split apart into this left half and this right half. So we can find the probability by joining up the left half working and the right half working together. Anything I missed? Yeah, okay. Probabilities. Sorry. Events can be partitioned into more than just one, like B happened and B didn't happen, like B and B complement. But I don't think we've really come across more than two partitions. But if the event that we ever do for some reason, it is the same idea. If we add, let's say, another bit to this, and this is, I don't know, BH, like BE, I don't know. There will be one part here, there will be one part here, and there will be one part here. So what this means is that if you want to find the probability of A, it's the same as you were doing just now. You've got A intersect B, you've got A intersect B complement, and you've got A intersect BE, which you can expand just like we did, just like we did previously down here. If we ever run into a third partition, which I really don't think we will, but you never know. Any other formulas for partitions? Okay, you cannot have partitions overlapping each other, because at that point you're not really splitting the space in half. Yeah, that's just a definition thingy. Okay, then, alright, so let's say we have, I think this shows up in a bunch of different questions, but let's say we have, a probability of, let's say we have we want to find A given B, but we don't exactly have the necessary information. And you would think to yourself, if only we could swap these two around, because we have the information for that. And we can. So let's use our Almighty formula from earlier. A intersect B over P B. This is the same formula from above. What I'm going to do now is swap A and B on top. Because if you have two events, you should draw it like that. A intersect B is still the same as B intersect A. And we can use that fact. So that's B intersect A over probability of B. Now, what happens if we split apart B using its partition of B and B complement? We can do that. That means that B will become we will split apart B using the partitions of A. Let me specify that. So we've got B intersect A and B intersect A complement. Because in our Venn diagram, you will have A and A complement, and then B will be in here. So there's this part of B, which is the first part, and then we've got the second part, which is this second part here. Now, we will use our almighty formula again, because we've got intersect, intersect, intersect. But our question has its information in like P given A given not B, things like that. So we sub in our formula one more time. B given A becomes, B intersect A becomes B given A times P of A. And you realize that the numerator has this part here. The denominator also has this part. So that's the same thing here. B given A, P A, plus, because we've got a plus over here, and this part over here, so we have P B given A complement, A complement. This is what we have so far. And you will realize that with the question's data, what we've managed to do is, from A given B, is swap it around, because now we have B given A, B given A, B given A complement. Now with the question, with the equation like this, you're able to sub in the question's data and calculate accordingly. That is what this giant thing is. What I've written down here is the exact same as what is over here. So you're using partitioning to go from PB. What is it? Partitioning from going to PB into this B intersect A complement, B intersect A, and then we use our almighty formula from above to make all the intersects into something given something times something. So once again, this formula is so extremely useful. I would say this is comparable to the star bang bang in linear algebra. This is the star bang bang of probability and statistics, at least for the first half of the topics in the trimester. This formula is like that important. Okay. Alright, next up is there's one example question I want to do. Kind of for myself, because I always get this wrong, but I think this warrants practice as well. So let's just do this one. Let's do it. I move my stuff over here. Alright, cool. 100%. Alright. So we've got our a machine, a factory uses 3 machines to produce certain items. M1 produces Okay, let's write a definition first. Let, oh, I want black, please. Let D be the event that an item is defective. M produces 50% of the items, of which 3% are defective. Let's write this out into numbers. First half, M produces 50% of the items. That means if you were to take any random item from the factory, there is a 50% chance that M1 produced it. So I'm going to put M1 is 0.5. Likewise for M2. M2 produces 30% of the items. So probability of M2, 0.3. Probability of M3 follows the same logic, 0.2. And here we've got this. Back to M1. M1 produces 50% of the items, of which 3% are defective. So is it defective given M1 or M1 given defective? Think about the order you received the information. What was known first? We have M1. M1 produced 50% of the items, which means that M1 produced this thing, of which means that you already know that you're considering items from M1. So it's given. Oh, I think I peaked the microphone. I'm so sorry. It's given that M1 is producing the thing you're inspecting right now, of which 3% are defective means that the probability, if I'm too loud at middle, the probability of that an item is defective, given it was from M1, is 3%, 0.03. Likewise, probability, same logic goes for the rest. 4%, 0.04. Defective given M3. I feel bad for this machine. It produces 20% of the items, but like 5% is all defective. Maybe that's why it's not as high, because the defective rate is so high, it makes it produce it less. Anyway, 0.05. Suppose that a defective item is found. What is the probability that it came from M2? Let's decode that statement into mathematics. Suppose that a defective item is found. So we are given information that a defective item is found. That means it's something given D, because it says, suppose that a defective item is found. That's what we're given this information. What is the probability that it came from? M2. So the answer that we're looking for in this question is M2 given D. You will notice here that we've got M2 given D, but here we have D given M2. If only we could swap those numbers around. Guess what? That's what we did earlier. Just like, where is it? We did it right over here. We had A given B, and we swapped it around, and we got B given A down below. And that's what we're going to do here. M2 given D. Let me put that to 100%. Let me write it over here. M2 given D, using our almighty formula, that is the same as this. And we notice here that we have probability of D at the bottom. We don't know what D is, because that's not what's given to us. That's why we have to use the partition formula, the part that breaks D into D intersect M1, M2, and M3. So we will swap these around. So we have D intersect M2. And at the bottom, we know that there's only 3 machines involved in this process. Wait, hold on. Did I miss anything in chat? Go to base theorem on Wikipedia and scroll down to interpretations. Quick side note. Base theorem on Wikipedia and scroll down to interpretations. Oh yeah, this diagram is really good. If what I've mentioned about base theorem still doesn't make sense, I think this diagram, which is fantastic by the way, because look at what they're using. Like, come on. Where is it? Oh. This is the best. We're in the best timeline. Beautiful. Stunning even. But genuinely, this is a very helpful diagram. If you don't understand what I've mentioned about base theorem, I highly recommend take a look at this diagram. Maybe not the whole Wikipedia page, because Wikipedia can be very verbose, but have a look. Anything else? Yes. Yes, I know, I did it. Like, I've seen the diagram before. But it really is a very good diagram. Back to where I was. We were splitting up this. We're partitioning D. So we know that this is our sample space, and we've got probability of D. And only 3 machines are involved in this process. M1, M2, and M3. That means we can split apart the sample space accordingly. We've got M1 over here, we've got M2 over here, and we've got M3 over here. So here we're trying to find the probability of D, which is this thing. And now let's take it part by part. We have D intersect M1, this part here. Now we have this part here, D intersect M2, and D intersect M3. Let's write that down. D intersect M1 plus D intersect M2 plus D intersect M3. The denominator is going to get real long, so be prepared for that. Now that we have everything in form of intersect, because we have D intersect M3, intersect M2, intersect M1, intersect M2. We'll use our magic formula to write them in the form of A given B. So we've got D given M2 times the probability of M2. These are numbers that we both have because they come from this sentence. This is probability of M2. This is probability of probability of D given M2. Probability that it's defective given that it came from M2. So let me write this all out. No, there's pen pressure on this thing, which I don't actually like. Okay, I think that's a good enough line. Probability of D given M1 times probability of M1, probability of D given M2, probability of M2. Once again, this section is the exact same as our numerator section. Probability of D given M3, probability of M3. And here comes the good old number subbing in process. D given M2, that is 0.04. Probability that it came from M2 was 30%. Oh, where did my cursor go? Oh dear. Ooh. M2 0.30. And we M1 0.03 times 0.50 plus. Since these two sections are the same, I can just copy the numbers from above. And then finally, we've got 0.05, I believe. And then 0.20. Yes, okay. Now we've subbed in all our numbers. All we got to do is throw it in the calculator and get the result. I hope I'm right after writing all of that. It says you got 0037. I'm going to put this in my calculator real quick. Okay, 0.04 times 0.30 times 0.03.5 plus 0.04 times 0.3 plus 0.05 times 0.2. She got, yeah, 32%. This number up here. I got 0.32, 432. Oh, it's repeating. 432 repeating. So that's one example question. I think this is a really good example question because it combines maybe not the independence part, but the conditional probability part and partitions. So I think this is a question that is a nice bit of a recap from this topic and the topic of beyond. Previously. There's the full working. If you want to take it in for a split second while I drink some water. Thank you. All right. Next up, oh, I need to put the splits. Where is it? Damn, that took like 20 minutes. Holy shit. Okay. Next up, we've got permutations and combinations. I don't think this will. It is in the topics list, so it will be tested. But I don't think this will be like a high mark kind of question. That said, I'm still going to go through it. I'm not saying I'm not. But I don't think the marks for it should be that high. Permutations and combinations. So what is a permutation? Okay. Permutation, usually it's written as, sometimes it's NPR or like PNR. There's a bunch of different ways to write it. For combinations, it's similar as well. You've got this, you've got C, N, and R. And then there's the one you see in the formula sheets, which is N choose R. But these are just different styles of writing the same things. So for permutations, a permutation is an ordered set of arrangements. What that means is that if you've got 3 items, 1, 2, and 3. Okay, let's say you've got 3 seats, and you've got 3 people that want to sit down. And it's not that, you can't just say that because these 3 people are sitting down, that that's the same configuration, because let's say they're A, B, and C. One combination could be A, B, C, but there could be another combination where A is in the middle, and you say it's B, A, C are its neighbors. This is a permutation because even though the elements are the same, the order mattered. The order was a different arrangement. So that's what a permutation is. It is an ordered arrangement of the elements. Basically, order matters. So how do you calculate the number of permutations of an object? The nice thing is that if you only have, let's say in this case, we have only 3 to choose from, and from those 3, you select 3 to be jumbled about, to be permutated. So it's 3 permutate 3. or if you want to write it like this, 3p3. The nice thing is that the answer for this is just 3 factorial. You just put an exclamation mark next to the number, and this is how many ways to rearrange them into different, distinct arrangements. But that is only if there is if the number of elements that you're choosing, in this case 3, is the same as the total number. If they are not the same as the total number, it's not n factorial. I mean, you have a calculator, so it's going to do this for you. I believe it's n minus r, I think. Yeah, okay, n minus r. So let's say in our early example, let's say we have 3 people who want to sit down at like the food court or whatever, but the table only has space for 2. So how many ways are there for 2 people to sit in distinct formations? That would be 3 permutate 2. It's not 3 choose 2, because A and B could be sitting at, let's say, opposite sides of the table, but we want B, A to be a different arrangement. We don't want to treat these two as the same. That's why we're using permutations here. So 3p2 would be 3 factorial over 2 factorial. In this case, that's just 3, because you've got A, B, B, C, and then, wait, 2 times 2 is 6. I get the feeling I've messed up somehow. But I do know that this is the formula. But we won't be using permutations that many times. It's only for this question like this, where you've got things in a certain arrangement and you need to be, the order matters. Like I've been saying it a bunch, but that's really what permutations are. You've got an arrangement of stuff, but the order in which they are in that arrangement matters. So that's what a permutation is. I've mentioned the formula already. Now we're on to combinations. Combination, commonly referred to as N choose R. This is where you have a bunch of items. Let's say you've got, I don't know, marbles in your hand, and you want to find out how many ways are there to choose. Like, how many ways are there to get sets of smaller marbles? If you've got 5 marbles in your hand, how many ways are there to get 3 marbles? You literally just do from 5, choose 3. 5, choose 3. 5, C, 3. So if you have, oh, that's my pen. Oops. Got 1, 2, 3. These are your marbles, and you want from 5, you want to choose 1, 2, 3 elements. The answer for that will be just from 5, choose 3. And you can punch this in your calculator to get some answer. If somehow you still don't know the button for that in your calculator, it should be listed as NCR. This is the button that will get you that answer. Then on the left you put 5, and on the right you put 3. Okay. Another coefficients, that's cool. They're commonly used in card questions, because you have like a deck of 52, and you usually end up choosing cards like how many aces can you get, or something like that. Conditional I've mentioned. Right. I think that's pretty much it for P and C. So let's try exclusion, inclusion, exclusion. So you've got the Venn diagrams. Okay. So usually we've got our Venn diagram like this. We've got A and we've got B. Here's our sample space. The inclusion-exclusion principle is just asking, what is this probability where it's A and B combined? For this, just looking at the diagram itself, we can probably hazard a guess that A union B will be some addition of A and B together. And if you add them together, you get probability of A, and then the probability of, oops, those lines are all in the same place, the probability of B. But as you can see, this red-black region has been counted twice. So we have to remove that excess in order for our answer to be correct. Maybe I should leave the lines there. So we subtract away the intersection, which was the part that we counted twice. This is the inclusion-exclusion formula. This is the actual one. I need to double check myself. Okay. Right, so this is the formula for 2 events. Now, if I draw the diagram out for 3 events, oh yeah, we've got 1, 2, and 3, A, B, and C. Same problem, we want to get the union of all of the things in the circles. Probability of A union B union C is, let's try adding them up like we did previously. And this will mean that this region will be counted twice, just like last time. This region will also be counted twice. This region will also be counted twice. So let's subtract them away, just like last time. A intersect B, A intersect C. Then we have probability of B intersect C. Now this, I'm not really sure how to show it, but now that we subtracted away the red stuff, we've taken away 1 time more of this special internal core than we should have. So we'll add it back in. So it is plus A intersect B intersect C. This is the inclusion-exclusion formula for 3 events. You add up the individual ones first. Then you subtract away the intersections between 2 events, between every 2 events. And finally, you add back the intersection of all 3 events. To generalize, there's like a really scary looking formula like somewhere, I don't know which slide it's in. It might be here. Okay, I don't think it's here. But it's like some scary looking like sigma thing, and then it's something to behold. But basically, if you're trying to find the A union B union C union D union whatever, it is the same principle as we've described earlier. Here we've got 1 event in our brackets, here we have 2 events in our brackets, and here we have 3 events in our brackets. If the number, okay, let's go through the 1 events. So same like above, we've got probability of A plus probability of B plus probability of C plus probability of D plus whatever. Inside these brackets, there was an odd number of events. Odd means plus in this case. I'm going to write that down. So odd number means plus. And therefore, even number would be minus. Same like above, we've got minus A intersect B. We've got 2 events in our brackets, so we put a minus sign according to this rule. notes back. So similarly, we do A intersect C, A intersect D, for every single intersection of two events. Now, we move on to the next one, where we have 3 events in our brackets. And 3 is an odd number, so we put plus. Probability of A intersect B intersect C, A intersect B intersect D, so on and so forth. What I'm trying to get at is, even though if you have a bunch of different elements, what it boils down to is the number of events in the brackets. If the number of events is positive, if the number of events is odd, like 1, 3, or 5, you put a plus sign. If the number of events in the brackets is even, like 2 or 4, you put a negative sign. That's basically what the general formula for inclusion and exclusion is. List out every combination of intersections, and if the number of events in those brackets are odd, like 1, 3, or 5, put plus. If it's even, like 2 or 4, you put minus. Yeah. I guess that's it for inclusion and exclusion principle. So now we move on to split. Move on to discrete distributions. Let me open up the lecture for that. That was lecture 3 and 5. 3 and 5. Okay. Then we look at our notepad. Okay, so next up on the topic list was discrete distributions. So what does it mean for a variable to be distributed? A variable just means, well, its value can change. It's when you perform a test and you measure the number of outcomes, and the number of outcomes isn't always the same. For example, when you roll a die, how many times do you get? When you roll 3 dice, how many of those times did you get a 6? That answer might be 1, it might be 2, it might be 0, or it might be 3 if you're insanely lucky. So that's what a random variable is. It is a variable with a random value. Now, a discrete random variable means that it can only have a certain range of usually integer values. Not always integer, but for the most part it can be. Let's say you can have 1, 2, 3, and 4. For our example, it was 1, 2, and 3. Let me put a 0, let's put it at the back. You can also have certain other discrete variables, like, let's say this function will only give you these exact outputs and nothing else. It could give you 0, it could give you 0.1, 0.3, or maybe 2.0. If these are the only outputs of that function, then we can safely say that, well, yeah, it's a discrete variable because these are the only things it can produce. There's no in-betweens. That's what continuous is for, but we're not doing that right now. So it's not to say that because it's a decimal, it will be a continuous variable. Not necessarily. Just double check the question. It tends to be the case that integers are discrete. That if you have an integer, it's a discrete variable, but just double check and make sure. Okay, next is discrete PMF. PMF stands for probability mass function, and it usually shows up like this. Trying to find the probability that, let's say in our triple dice rolling example, it is the probability that the event happens this many times. So the probability of 2 will be the probability of x equals to 2. This means that we got 2 6s in our 3 rolls of rolling the die. So PMF is just a function that will return the probability of that many events occurring. P of 2 means that the event X occurred 2 times. P of 0 means that the probability that means that it will return the probability of the event X happening 0 times. So yeah, that's what a PMF is. The cool thing with that is sometimes, let's say we've got 0, 1, 2, and 3. If I draw 0, 1, 2, and 3, some outcomes are more likely than others. Let's say 0 only happens this many times and 3 only happens this many times. Actually, no, 3 can only happen like this many times if you think about it. It'll be like this, I think, for our example at least. And this will be the values of X, and the values up here are the probability P of X. And let me just move the graph. This will be X. So that means that this is P of X equals to 0. Alternatively, you just put small p 0. That also works fine. This is what our probability graph is looking like. Now, there's also this thing called the CDF. If I'm not wrong, that's the cumulative distribution function. But the keyword here is the C, cumulative. It starts from 0, or whatever your lowest value is. Here, in this case, it's 0. And adds things up. Here we've had, this will be, okay, let's just assume that, let me just give this random probabilities. This is 0.4, this is 0.3, this is 0.2, and this is 0.1. That might actually be the case for our example of rolling 3 dice, but let's just work with it for now. So these are our px values. A CDF, usually written as a capital F, means that it wants to sum up all of the previous values up until that point. So, I don't know, all previous x. You want to sum them up. So in this case, if you wanted to find f0, that would just be p0 because there's nothing else before 0. But f1, because f is cumulative, CDF, cumulative distribution function, it would include p0 and then also p1. Likewise, f2 would be p0 plus p of 1 plus p of 2, because it's the number mentioned plus all the previous probabilities. It's cumulative. And finally, we have f3, which is the biggest value that our variable x can take. And the cool thing is that, because let's say we drew our graph up here, we know that x will only have a certain range of values, 0, 1, 2, or 3. Which means that there's no event after 3. There's like nothing here, nothing at all. So that means all the events that can possibly happen would have finished happening at 3. So if we were to add up all the probabilities, it should be equal to 1. Total probability is 1. Because there's nothing else after 3. So let's say you're doing a CDF function and you want to check if it's alright. You can go to like the maximum value, in this case it's 3. And you should like make sure that this will be equal to 1. Because this is the maximum value. Because there should be nothing else outside this range. Once you've hit the maximum, there's nothing to add, there's nothing to accumulate. You just plus 0, plus 0, plus 0, plus 0, which is still 1 by that rate. Sorry. So that's what a CDF is. It's cumulative. It adds up all the previous probabilities it has encountered so far. Next, we'll be heading on to discrete distributions. Discrete distributions, the different types of discrete distributions. You've got 4 main characters. Really only 3, but as a formality, I'll do the 4th one as well. Bernoulli is kind of laughably simple. What it is just a single coin flip. That is it. A Bernoulli trial is something that happens once with a certain probability. I'll just double check to make sure I'm not spouting nonsense. Yes, so a Bernoulli trial is like flipping a coin. Flipping a potentially biased, maybe not, coin once. You flip a coin once. So it could be biased, it could not be biased. But the important thing about the Bernoulli trial is that it happens once. So the probability of, let's say you get heads, is some probability p. And the probability of tails, which can be considered as success or failure, will be 1 minus p, because total probability is 1. This is what a Bernoulli trial is. A coin flip that you either succeed with a certain probability that's constant, it doesn't change, or it fails with 1 minus p. That is what a Bernoulli trial is. Yeah. If you want to formally write it, it could be something like this. X follows a, that's what the tilde means, it just means follows a. And then you write down the distribution name, Bernoulli. I think I spelled that wrong. And then you put the parameters. In this case, it's the probability of success, P. You'll see a lot of this syntax. So it just means that X is a variable. Like decoding this from math to English, it just means that X follows a Bernoulli distribution with probability P. X follows a Bernoulli distribution with probability P. Next up, we have binomial. This is the one that you'll probably be working with. For binomial, you've got two parameters. You've got the number of trials. This is usually denoted as n, and probability of success is usually denoted as p. Binomial can show up in a bunch of different places, but to apply a binomial distribution, there are two main criteria that have to be satisfied. Number one is that every single trial is independent of any other trial. When you flip a coin, the fact that you flipped it the first time shouldn't change the probability for the second flip. That would not make sense. So I'm just going to write independent trials. And the second criteria is that the probability of success must not change. It must stay constant throughout this whole experiment. So I'm going to write constant P. Now the formula for this is, if you have, let's say we are doing how many heads you get for a total of, y is a random variable that follows a distribution of binomial. I'm just going to write b. Let's say there are 10 coin flips, and the probability of success was 0.6. Maybe it's a biased coin. You want to find the probability that with this biased coin, after 10 flips, you will get 5 heads. The formula for this would be, there are 5 heads, so let's see if I were to draw it out. You have coin flip 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. You want to find the probability that 5 of them succeeded. So let's say it's 1, 2, 3, 4, and 5. It could be this 5, or it could be this 5, or it could be 1, 2, 3, 4, and 5. You wouldn't know which 5 exactly succeeded. You just want to know that 5 of these guys succeeded. So from these 10 outcomes, we want to choose 5. 10, choose 5. Then we write, we want to make sure that these 5 succeeded, that we actually got heads. So we put 0.6, which is the probability. And we succeeded 5 times, so we put 5 over here. Because we succeeded 0.6, the next success is also 0.6, so you times 0.6. And you do that for every single success. That will guarantee that 5 have succeeded. But you also want to make sure that the other 5 are not successful, because you want 5 successes and 5 failures, because the total number of trials is 10 in this case. So the probability of failure is 1 minus 0.6 in this case. 10 minus 5. You want the other remaining parts to fail, just to guarantee that you will end up with 5 trials that succeeded. This is the binomial formula. It'll probably show up. I think there's a non-zero. It's a very high likelihood. I think it will show up. Yeah, I think that's it for binomial. I don't think I missed it. This is the formula with more algebra in it. Okay. So that was binomial. Now let's go to geometric. This is the next kind of discrete distribution. So a binomial trial is used when a certain event either happens or it doesn't. You either succeed or you fail. Geometric is similar, except this is for distributions or probabilities where you fail continuously until you succeed once at the end and stop. It's like that lottery question from the tutorial. You keep trying at the lottery over and over and over again until you succeed. Once you succeed, like, you got the money already, so there's no need to try again. Unless you're like, that human is exceptionally greedy, but we're not talking about human greed right now. But geometric is used when you have a trial that will succeed or fail. If you succeed, great, you can stop there. If you fail, you will try again. You might succeed, you might fail. And if you fail, you try again. You succeed, great, stop. If you fail, try again. So on and so on. So you can see that after success, it's guaranteed to stop. This is what a variable that has a geometric distribution does. Usually it is written as x follows a geometric, and with a certain probability. This is the probability of success. Let's say it's 0.6 again. I think it's 0.7. Let's be cool. This means that, okay, so if you want to find the probability that, let's say this was a coin again, the probability of this bias coin showing up as heads was 0.7. You want to find the probability that on the third flip, we finally got a heads. So that means we failed at getting a heads the first time. We failed here, and we only succeeded the third time. So if I write out the probabilities on this diagram, we've got 0.7 here. We've got 0.3 down below. Now, if you want to find the probability that it happened on the third time, oh my god, okay, sorry. The probability that it happened on the third time, x equals to 3, means that we started here. This is the entry point, this is the main of our program. We failed once, so that's 0.3. Then we failed again, which is 0.3 again. But on the third time, we finally succeeded, and that's 0.7. So 0.3, 0.3, 0.7. This is the probability of x equals to 3. This can also be written as 0.3 3 minus 1, 0.7. I'm writing it this way because we succeeded on the third try. That means for the previous trials, trial 1 and trial 2, we failed. So for all previous trials, that's what 3 minus 1 is, we fail, which is 1 minus 0.7. Oh, if you hold the line, it becomes straight. Oh, interesting. And then we only succeeded on the third trial, which is the 0.7. So this is the formula for a geometric distribution. If you have equals to n, you have failed a certain number of times, but at the very end, you finally succeed. This is the formula for a geometric distribution. Next up is Poisson. Oops. Come back. There we go. We've got the Poisson distribution. You can think of this as like, I like to think of it as like a spicy version of the binomial distribution, because they are similar-ish in the sense that you've got a bunch of events, true or false, but and you're trying to find the probability that it happened, given the certain probability of success or failure. Poisson is great when it comes to scale, because let's say you have you've got a huge number of trials, like you commit something, you do something 10,000 times, and you want to find the probability that it happens 3 times in a certain duration. You would have to evaluate this number. And that means putting 10,000 factorial in your calculator, which is absolutely ridiculous and mind-boggling, and none of our handheld calculators can do this right now. So, to mitigate this, Poisson comes into play, which is the spicy version of binomial, where we write it as this: x follows a Poisson distribution with parameter lambda. What in the world is lambda? When converting to and from binomial, lambda is equal to the number of trials in a binomial distribution in a binomial experiment times the probability of success. Lambda equals MP. You can usually think of this as the rate that something happens, because given a certain number of trials, it occurred so many times. So if an event happened 3 times per 100 trials, lambda would probably be 3 over 100, which is 0.03, because lambda tends to represent the rate that something happens. Yeah. Yes, lambda. So this is how you model a Poisson distribution. And the formula, which, I mean, if she's going to test Poisson, she's going to get the formula. There's no way, I don't even know if she remembers the binomial formula. I mean, she probably does. The probability that x equals to some certain number would be, I'm just copying from the sheet at this point, lambda x over x factorial e power minus lambda. This is the formula for a Poisson distribution. So if your event happened twice, that will be x equals to 2. So you would change, oh, this is not x, it's meant to be n. You would change these n's to be 2. However, you can't willy-nilly just use Poisson because your numbers are like too big for you or whatever. You have to fulfill a certain criteria that allows you to convert from binomial to Poisson, and that allows you to model a binomial distribution as a Poisson distribution. The 2 conditions are that your n from your binomial must be large. It has to be like 50 or something. I'm pretty sure. Yeah, n must be 50. And the second condition is that your rate, your lambda, which is n times p, must be lesser than 0.5, oh, oops, 10. Why these conditions exist, I have no clue. It's just what we have. But you need to make sure that these must be fulfilled before you use a binomial distribution as a Poisson distribution. So those are our four main characters. Bernoulli. Let me scroll up. Damn, there's a lot of stuff. Oops. We've got our Bernoulli distribution, which is flipping a coin once. The coin could be biased or not biased. And then we've got binomial, which is our common thing. This is the what's that saying? Yeah, this is binomial distribution. This is our common distribution. Here is the formula. Given a certain number of successful events, we can find their probability by choosing that many number to be successful and making sure the remaining elements fail. So that's why it's 1 minus probability of success over here. Next is geometric, which is try, and you keep failing, but at the very end you succeed, and once you succeed, you stop. Which is why I find that this diagram helps a bunch, with success on the top and failure at the bottom. So once you've hit a success, you've succeeded already, so you can stop. And the formula for this is n minus 1, because if you took 3 tries to succeed, that means your first 2 tries failed. So it's 1 minus p times the number of times you failed, and finally times p because you succeeded at the very end. Lastly, we have Poisson, which is the spicy binomial. Make sure you fulfill these 2 criteria before you're able to say, yeah, I can use Poisson for this. Then we have expectation. Here we're using a discrete variable. So what it means for the expectation, first of all, expectation and mean are the exact same thing. There is literally no difference between the words expectation and mean. So expectation of a certain random variable is the same as the mean of a certain variable. And this mean is given in here, I think. Oh, oops. I'll get it closer. This is the formula sheet that will be given in the papers, in the final paper. We are given the mean and the variance. Mean is the exact same as expectation. So for every single distribution that we've kind of worked with, there's the mean and variance right there, the expectation and variance. So we don't have to memorize this, thankfully. Now, what does it mean to have the expectation of something? It just means that to calculate the expectation, this is for every value that x can take. So for every value, you want to sum up the value times the probability. Value times probability. In our case earlier with the rolling 3 dice and getting how many 6s, let's calculate that right now. So if we rolled that many dice and we just didn't get a 6 at all points in time, that means that we got a minus 1 over 6 times 3, because we rolled 3 dice and we failed every time. So this would be the probability that we get 0 6s plus 1 times, we got 1 6. So that means that we've gotten 1 over 6, and we've gotten 1 minus 1 over 6 twice. We succeeded once, we failed twice. But it could either be success, fail, fail, or success, fail, fail, or my favorite, fail, fail, success. I just realized what this is an acronym for. That's funny. But we've got 3 positions, and only one of it is a success. So from 3, we choose 1 to be a success. You may recognize this as the binomial formula, and that's correct. It is binomial. likewise. So let's do the case for 2. Here we succeeded twice in getting a 6 in our 3 dice rolls. So we put 2 here, 1 minus 1 over 6. That happened once. From 3 positions, we choose 2. There's also technically a 3 choose 0 here, like right here, but 3 choose 0 is still 1, so it's not there. And then finally, we've got getting 3 6s for 3 of our different dice rolls, which is insanely lucky. It's like, what is that? 1 over 216. That's like 0.04%. Insanely lucky. And this is 3 choose 3, which is just 1 at the end of the day. What I was doing this whole time is that I'm following the formula up here. Its value, in this case x, times probability. For our first case, our value was 0, and the probability of that was this number here. For our next case, our value was 1, and our probability was this case over here. Then when our value was 2, we've got this probability over here. And finally, when our value was 3, we had this probability over here. I'm not going to calculate this, but I'm sure it's a perfectly fine number. So that's how you calculate expectation of a variable. At the end of the day, like I mentioned a bajillion times, it's really just this. Value times probability. Now, what if you need to find something else relating to the variable, like e of x squared? You'll find this very commonly when trying to get the variance of something. As always, it is for all values that x can have. In this case, we have x squared, so it's value times probability. Whatever is in these brackets, you just Control-C, Control-V, and you put them here. That's all that it is. Oops. Yeah. Then next up on the list is expectations. Yeah, so if there's any other thing they want you to find, let's say they want you to find expectation of 2x, for example. You just literally do, for all x variables, you've got 2x times the probability of x. And you will get this. Take whatever's in here, Control-C, Control-V. But in this case, here it's 2 times x. This will be wait, let me check the slides. I think I've missed something. This is how to find expectation. Yep, here's the value times probability I've been mentioning on and on and on. These are formulas that are given in the formula sheet, so you won't need to memorize them. This is what I was saying, where whatever you have in the expectation brackets, you just copy and you paste. That's it. Okay, these are different formulas as well. These are just called the addition formulas. Let's say you want to find expectation of 3x plus 6. And you absolutely could do this, like we've always been doing, but this would take quite a lot of work. What if we already knew the expectation of x from an earlier calculation? Could we somehow reuse this to get this? Absolutely. That's what these formulas are for. Let's take the first one, for example. We've got a pen. So we've got expectation of 3x plus 6. Using these formulas, we can take out the constant, which is 6 in our case. Yeah. So 6 plus expectation of 3x. We can simplify this even more, because you can like take out the 3 and you get expectation of x. And this is a value we probably already know by this point. So you save a bunch of computation instead of having to do all of this stuff again, which would suck. You can just reuse the value that you already had before and calculate it this way, using the addition formulas here. You can, if you have a number, 6 plus x, you can just take out that 6 basically. And if you have a scalar being multiplied with your random variable, you can move that scalar immediately outside, which is what I'm doing here. E3x is the same as 3 times e of x, which is great. There is also one for multiplication, but you have to take note that this is for independent variables only. You cannot use this with dependent variables. Only if it's independent are you able to use this formula. Because later in like covariance or correlation, you learn that there's like another term that hangs around when you do this. But for independent, it's not there, so it's okay. Yeah, that's expectation, mention addition formulas, multiplication. Next up is variance. So for variance, expectation and variance are like twins, I guess. They mean different things about your data. So an expectation is what's the average, what's the mean value that you're gonna get. So in our dice example above, I think if I calculated the example, it would have been like 0 point something. Because when you roll 3 dice, chances are you're probably going to get 0 a lot of the time. So that means that on average, that I would get 0 most times when I roll 3 dice. So expectation of a variable, which is the same as mean, is just the average of what that variable is. On average, if I roll 3 dice, I will get 0 sixes. Variance is a measure of how much that data is spread apart. I'm not super good at like visualizing this, but from what I know, let's say you've got your data peaking around a certain value, or maybe like the example we had earlier, like a staircase like this. Your mean is probably around here. Variance is how much that data spreads out on both ends. This is best seen with a bell curve, like that. Oops. Nope. Alright, trust. Where your mean is in the center, and variance is how much your data spreads out on both sides. If your variance is really small, you will have a sharp peak, then a fall. Because if this is your mean, mu, most of your data is within one like range. This range is called the standard deviation actually. But most of your data is contained within one range. If your variance is large, you get a big fat bell curve like this one here, because there's a lot of area underneath that's not within one range. Not within this range, I guess. So variance is how much your data spreads apart. Variance has 2 main formulas. First one being the one you've seen and probably worked with a lot. This is the main formula. But there is also the other one, which I actually got tested in the quiz, I think. I'm pretty sure I forgot that one, which is sad. X minus mu. X minus mu squared. I think the square goes here. X minus mu. So we've got. I need to remember where the square goes. Okay. The square doesn't go here, it goes here. Yeah, this is the second formula. but like 95% of the time you'll be using this thing anyway. It's just easier to calculate. Now for variance, you can also add and subtract like expectation, but it's a little bit different. Oh, and also there's a standard deviation. If we have the variance of x, the standard deviation is usually written as sigma. Just add of x. This is always equal to the square root of variance. Forever and always. There's no other formula, there's no other tricks. That is what standard deviation is. Okay. We've got this formula I've mentioned already. This is the addition formula, kind of. If you want to find the variance, earlier we found the expectation of where is it? 3x plus 6. So let's work with 3x plus 6. So we have the variance of 3x plus 6. Now, according to this formula, we're right now at this stage. And if you think about it, this plus 6, if our original data was, let's say, like this, with our original mean mu here, once we plus 6 to every single value, all it does is that if this was the original mu, it just shifts everything over by a certain amount. And this becomes mu plus 6, because every value got added by 6. So it moved the data, but the spread of the data didn't change. That's why we're able to say that this is equivalent to just variance of 3 times x. You shifted the data, but you didn't spread it out more. So there is no change in the variance, because variance is the measure of how spread out your data is. And now that we have that, we've got 3x, variance of 3x. If we have a constant here, when we take it out, we need to square it. We have to square it. Be sure to not forget this. Yeah. So that is the quote-unquote addition formula. Now for the actual addition formula, you can only add variances if they are independent. So that's what she's put here, not working for all. What this says is the variance of a bunch of stuff that you sum together, if they are independent, that means they are the same as the variance of, that means it's the same as adding the variance of every single independent variable. I'm not sure if we're going to use this. I don't think we ever have, but it's something that's there. There's the formula sheet. Yeah, and once again, standard deviation. At all points in time, this will never change. Standard deviation of any variable is just square root of the variance. So that's the formula for that. Okay, I'm going to have water for a quick second. Anything in chat that I missed? I don't think so. One of my best friends from secondary school suddenly spawned in chat, which is why I may have laughed earlier. Okay. Next up, continuous distributions. Let me just remove all this. Continuous distributions is not this, not this, not this, but instead we've got this and this. Oh, okay. Alright, so earlier we mentioned discrete random variables. Continuous random variables are a bit of a variation on that. Ideally, the idea behind it is still the same, the underlying idea. So, one of the most common examples of a continuous variable is the height of a population, like the human population in a certain region. So, let's say we take the height of humans in Singapore. That means you've got a bell curve of height in cm, and here it's the probability that you will meet a human of that height. And this ends up being like a normal distribution, a good old bell curve. Technically, there'd be two bell curves because men and women are different heights, but let's just assume it's just one. This is a continuous distribution because let's say the mean is at 165, I guess. 165 isn't a discrete number. You can have 165.1, 165.2, 165.21. There's lots of in-betweens here. So you can't have the probability of exactly 1.65. What the best that you can do is make a small rectangle here. I think it's probability density. I think that's a better way to put this graph. And this area here is an approximation of how many people are 165 cm. Because you cannot do this. In continuous distributions, the probability at a single point with an equal sign is always defined as 0. You can never use equals when it comes to continuous distributions. They always have to be ranges. That's why this rectangle exists. You have a little plus minus going on. So you have maybe 164 to 166. And that will be some certain value. Because you're finding the range from here to here. And that has an area. The area under a graph like this is the probability that it exists, the probability of that event occurring. So between this 164 and 166, this area is equal to the probability that you find the person that is 165 cm. So that's what a continuous random variable is. Just make sure that you never use equals. Because if you do, that probability is equal to 0. It doesn't mean anything in a continuous distribution to take the probability at a single point. Next up, we've got the continuous PDF. Here it's PDF, probability density function. That is, oh yeah, I was right to write probability density here. This gives you pretty much what the probability is for this kind of range. Like as the limit of this range size goes to 0, what that value ends up being close to. Let me check whether I got my terminology right. PDFs are not probability. Yeah, this is what I mentioned earlier. You cannot use an equal sign. Probability of equals anything is 0. You can only talk about ranges. So PDF is a probability density function. This is right. So we're talking about how probability can only exist in ranges. So we're trying to find a function, a PDF, which is also written as this, x, which is how probable is something between this event, between 164 and 166, how likely is it to occur? And I mentioned earlier that the probability is the area under this graph. So, and what is the way to calculate the area under a graph? an integral. But I will double check because I'm I received a message from someone earlier. I just want to make sure that my wording is completely unambiguous. Where is it? Right, so someone asked earlier to Elin, is there completely no integration at all, or is it for this? She replied with the phrase, I quote, no integration, close quote. So there is no integration at all, seemingly, hopefully, probably. So yeah, I guess there's no really need to go through this. But concept-wise, the probability is between a certain range. In this case, we have 164 and 166. And then there'll be something here, some function, f of x. There'll be some function that determines what the probability density is. But to determine whether that function, this p of x, is even valid, it needs to uphold two conditions. The first condition, the two main conditions, is that the values that get spat out, the values that get spat out from p of x must always be non-negative. You cannot have a probability that's negative. That doesn't make any sense. Oh, my cursor's acting up. Okay. Yeah, you cannot have a negative probability. And by extension, you can't have a probability that's like more than 1 as well, but I'm pretty sure that's understood. But that said, if this represents the probability, if you consider every single possible value, and because this is continuous, we can go from whatever its minimum is to whatever its maximum is. So its minimum will be put at minus infinity and maximum will be put at infinity. This is f of x. Yeah, okay, sorry, this is f of x. This isn't p of x, this is f of x. When you have a function that tells you the probability, if you sum up everything, you've encountered all your possibilities already, so the probability will just be 1. These two conditions can be used to test if a PDF is actually a PDF or not. It must fulfill these two in order to be a valid PDF. Just a quick side note, regarding the signs, the probability that, let's say we have our example from earlier, 164 to x 166. Because we're talking with continuous variables, and we mentioned earlier that it doesn't make sense to have probability at a single point, only for continuous variables it is okay to discard or add the equal signs. They mean the exact same thing. This statement is equivalent on both sides. Even though I remove the equal signs, because this is a continuous distribution, it doesn't make sense to have probability at a point, so you can just safely remove the equal sign. Likewise, there's CDFs that also exist, cumulative distribution functions. They are also used as a capital F, and earlier for discrete, it was like the sum of all the previous values up until that point. It's similar here. This is the formula for this. Unless I got that wrong. But I don't think she's covering it anyway because there was no integration. Yeah. Okay, so that is the formula for this. Don't know if she's going to use it. There's no integration, so we'll quickly move on from that. Oh, I didn't. Alright, that bit was late, but oh well. Next up is the different kinds of continuous distributions that we may encounter. We've got the uniform distribution, which we've used a couple of times. The uniform distribution just means that for a certain range, let's say from I don't really have a very good example for this, but you have a certain range. This is your value line. It's maybe units or something. you've got a certain thresholds A and B, where outside A and B, there's zero chance this thing happens. There's no way. But within A and B, we know that the chance that this event happens is the same. It does not change from A to B. It will still happen, but all the probability will be the same. So if you were to draw the probability density graph, it would look something like this. And since we know that the total area under the curve for any probability should be equal to 1, we know that the area of this is 1. And since this length is b minus a, we can calculate that this is 1 divided by b minus a. And that's exactly what the formula for a uniform distribution is. I'm skipping anything important. I hope not. Right. 1 over b minus a. That's exactly what I've written over here. To write this down, we write this x follows a uniform distribution, and then inside we have the range. So we go from A to B. And the probability that the event happens can be calculated just as easily. So it's just B minus A. Let me just make sure I didn't miss anything in this surprisingly large section. Cumulative. The CDFs and PDFs will be given in this kind of format. It's like a piecewise thing. So it's 0 for some range or like otherwise. And other times they'll give you, it'll follow this function between this range and this function between this range. So when you're trying to sub in values, make sure you use the appropriate range to get the proper values. That's an example question. Okay, yeah. So that's a uniform distribution. And now comes the main character of statistics, the normal distribution. This is typically written as x follows a normal distribution with a mean and a variance. Mean is usually mu. Variance is standard deviation squared. As you know, this is variance of x, I mentioned earlier. But the thing on the right-hand side of this bracket is the variance of a variable. Just like our formula sheet said. Don't have the formula sheet with me, but that's fine. I don't have it open at least. So this is how you write the thing for a normal distribution. You have mean and you have variance. And for the slides, all bell curves follow this kind of family of functions. There's no way we're going to be tested on this specific function. I don't even think she remembers this specific function. But this is how you get that shape of a bell curve. What's important to know is that this is any generic normal distribution, but there is a special version of this called the standard normal distribution. This has a very particular shape, I guess, where the mean is 0 and the variance is 1. It's called standard because it's every normal distribution can be shifted to the exact same exact same version to it. So every normal distribution can become a standard normal distribution. This can be done by x followed this earlier up here. So let's go back to our height example. We had something like this. To shift this into the standard normal, what we will do is we take x and we minus mu. This takes the bell curve, which could have been like, let's see, 0 was like here. The bell curve could have been like this. Mu was over here. After shifting with x minus mu, it will be centered at 0. That's the step that we're doing over here. And then after that, we divide it by its standard deviation. This is to make sure that the data is evenly spread out. Sorry, not evenly spread out. To make sure it's spread out like how a normal distribution, a standard normal distribution would have it. So x minus mu over sigma, or over standard deviation. Likewise, you do the same for the other side. Pen, why don't you go pen? 165 minus mu, you might have some number, it might be like 166 or 170 or something, and its standard deviation. Sometimes sometimes this section here is written as just z, and this will be 165 minus mu over sigma. You should be given these numbers, so you probably get some kind of decimal like 0.5 or 1.3 or minus 2.6, but you will get a number on the right by that point. This is the same as phi of whatever number you get on the right. If you have z and you have less than, or maybe less than equal to, in this case it doesn't matter because you're using a continuous variable. If we have this formation and we have this number on the right hand side, it is the same as this phi of the certain number. What does phi mean? It is just the CDF of the standard normal function. So if this was the standard normal function, and you have some value, x, I guess. So let's say this was x. That just means that this is the position that it is on this graph. Phi is the probability that from minus infinity to that point of what it could be. So the probability that you find someone under the height of 165 is you take the shortest height possible and you just go all the way until you hit this x threshold. To find a range, this is usually when it will be something like 163 x 165. It will be something like this: 165 163. What this is doing is, if you have a range, say this is y over here, we're trying to find the range between x and y. So what we want to do is, x is this giant black shaded region. We want to minus away this red shaded region. And we can do that by finding y and finding the phi value of this thing. So this will be, this will be phi of 165 minus mu over sigma. This is how you make it to a standard normal. And similarly, you get 163 minus mu over sigma. This is how you find the probability of a range. Standard normal exponential. Yes. So phi is just the to get the values of phi itself, you will have to be given a table. If she doesn't give the table, I think you can leave your answers in terms of phi, and that's completely fine. Because unless you somehow remember, where is it? Not this one. Unless you somehow remember this one, this specific formula, if you memorize that, then you would be able to get the phi values, but no one's going to memorize that. She's not going to memorize that. The only way to do it is if you're given the Z table. To use the Z table, you just check the decimal places. So let's say if this was phi of 2.2, maybe 1.2, the table will be something like this. You would have 0.1, 0.2, 0.3, so on and so on. You would have 0.01, 0.02, 0.03, so on and so on. You need to check for your first decimal place here and your second decimal place here. and where the rows and the columns meet is the z value you're looking for. That is how to read off from the z table. Oh, that was quite a bit. I think I mentioned a bunch of stuff I wanted to mention later, but that's fine. The last continuous distribution that we're working with is exponential. I think we've used this like exactly once, but even still, an exponential distribution. Did I miss anything? I mentioned this. Normal distributions are symmetric, so that's pretty cool. So whatever's on the left of mu has the same shape as whatever's on the right of mu. Mu is always the center of a normally distributed variable. This is the z table. This is how you standardize. Minus mu over sigma, that's what I mentioned earlier. Okay, exponential distribution. So to write it, it would be x follows a exponential distribution of some parameter lambda. We have no clue what it is. The probability, this is its PDF. Which I guess it's neat, I guess. Model the distribution of very rare events. Interesting. That's the same as Poisson, where your n is so large that it doesn't really make sense to use a different kind of distribution. So that's when we tend to go to these lambda stuff to do that instead. Yeah, okay, I guess that's it for the different kinds of distributions. There's the formula sheet I mentioned earlier. Let's pull it up again. So now I've talked about all these 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7 main characters of statistics so far. But normal is really the main character of all of them. We've given all their mean and variances, so there's no need to calculate them out by yourself. As long as you're given the parameters, these guys in the brackets, you should be able to find the means and variances. Expectation. To find the expectation of this, what you tend to do, we're not integrating, I'll just reiterate that, but for the sake of a quick, just telling you what it is, in case, I don't know if it comes out in some weird way or not. The expectation of a continuous random variable, okay, for discrete, it was something like this. We had all x, value times probability. It's always been value times probability. This is for discrete. For continuous, it is the same idea, except now we don't have a discrete set of values that you can take. There's a bunch of variables that you can take. Like for the height example, it could be 164, it could be 164.5 cm, it could be 163.5 cm. There's a bajillion different values you can have. So how do you sum up infinitely many values? That's where the integral comes in. So from its minimum value to its maximum value, same as always, value times probability. In this case, it's f of x. Once again, we're not integrating, but I'll just let you know that this is what the formula for expectation is. Which doesn't seem to be here. Oh, it's here. Yeah. From its min to its max, value times probability. Just the same as it's always been, except instead of a sigma, you've got an integral sign. Variance can be calculated the same way. The previous formula of variance of x being this formula still holds, thankfully. So you can just use this formula to calculate variance. And likewise, if you ever need to calculate e of x squared for a continuous variable, it's the same as the above. Whatever you have inside, you just copy and you paste it. This square is the same as this square. You just copy and paste. That's expectation. For variance, you just use the same formula. Standard deviation, same as always. The standard deviation of any variable is the square root of its variance. Expectation given, you don't look at that. Variance. These are the formulas if you really want to integrate it, but please don't do that to yourself. Let's just use this one here. Independent variables. Okay, this is what I mentioned a little bit earlier about the addition formulas. Only if they're independent can you add up like the variances. The variance of a sum of different variables can only be equal to the sum of all the individual variances. This only applies if they're independent. Otherwise, the same rules still hold from discrete random variables about how to add and subtract and modify values. Like if we had the same expectation of 3x plus 6 thing again, even if this x is discrete or continuous, it will still hold the same ideas, and you will still end up with this when simplifying. Anything else in the slides? Formula sheet given. This is what I'm saying. If you have a thing, the g of x, that's the thing you copy and paste. Copy and paste. That is literally not there. Okay. Right. So that's done. Pretty sick. Now, this next part I am not so sure because we've got. I'll put that there. The formula, the topics list on Teams, once it goes from continuous distribution, it goes straight to CLT and likelihood. It has no mention of joint distributions and covariance and correlation. So namely this, and kind of also this as well. But this is just how to add stuff. I think this is still okay to look at. But it's not really a main topic. It's these two. So this and this aren't mentioned in the topic sheet at all. So I'm just not going to cover it. I don't think it'll come out. If it does come out, I don't know why she put it. She skipped it in her topics list. Okay, next. CLT. Let me make it a one screen thing. Then we go here. Okay, I mentioned what phi is. I've talked about the z-table. I've already mentioned that this is how you indicate a variable that is normally distributed. You have mean mu, and you have variance sigma squared. So this is the main way to write one variable that is normally distributed. Now, this is an open-ended question, so this is probably where the big marks are. I've mentioned phi. I talked about that's okay. That's also phi. This is where the mu and sigma square come from. So it's mean and then variance. Mean and variance. The law of large numbers basically says that because if you find the average, let's say you have a population. Let's say you have a population of people, like the population of Singapore, for example, and it'd be horribly unfeasible. It'd be not feasible to ask everyone in Singapore, do you like pineapples on pizza? The correct answer is yes, but people won't say that. So it's not feasible to ask everyone this. So what we do is we take samples, because you can ask maybe 100 instead of the 6, 7, 8 million people in Singapore. So you take a sample of 100 and you ask these 100 people, do you like pineapples on pizza? And you will get a certain number. You say yes or no or something. Maybe not. think I should have used a different example question. But the idea is that you take a sample, and from that sample you gather some data. Maybe it's maybe they rate pineapple on pizza. Maybe they rate pizzas with pineapple on them from a scale of 1 to 10. In that case, it's like continuous. So like you can give a score of like 6 or 7.8 or whatever, but they will give a score. And if you take a sample and you ask these questions to everyone, they'll give you a score. And if you take the average of that score, you get something called the sample average. What I'm getting at is that the law of large numbers says that if you take enough samples, many samples, and you keep computing the average, if you take your samples and you increase the sample size, as you keep doing this process, your sample average will eventually approach the true average of the whole population of Singapore. That's what the law of large numbers means. So you've got an average. These are all the individual scores from people from like 0 to 10. And you find the average. And of course, you ask these people to make this work. You have to make sure you ask them by themselves. You don't ask two people together, and because one person says they really like pineapple on pizza and they rated a 9.2, the other person, their friend sitting next to them, will be like, oh no, I don't want to lose them as my friend, so I better give them a high number. So you have to make sure that every time you ask them, they are independent of each other, which is what the independence means in this section here. And to be identically distributed means that everyone has a somewhat decent chance of saying, giving the score that they're going to give. IID means independent and identically distributed. So once you have a large number of samples that are independent and identically distributed, then the law of large numbers can kick in and say that if you ask many people and you find the average, your average will end up being super close to the genuine population average. That's what the law of large numbers means. This is like just proving why that's the case. So expectation of the sample is all this. Since this is a constant number, we can factorize it out. And all of these are still from the same distribution, so it's mu plus mu plus mu plus mu. So it just becomes n times mu. And since we divide that by n, it just becomes mu. It will cease to be random because you approach mu at infinity. CLT. This is where, now we're at this point, sample mean and average formula. This is where this comes in. So we know that this is the distribution for the whole population. And then we took a average. We asked a bunch of people, and now we're taking the sample average. So we asked 100 people, we added up all their scores, and we divided it by 100. So I'm going to write sample 100. And as we mentioned before, because we took an average of a bunch of people, 100 is still pretty large. So we can safely say that this will be mu. Our mean, our average, our expectation will not change. That still stays the same. However, our variance now becomes this, sigma square over n. This is an important formula to remember, so please do take note of this. Personally, I like writing it as this, mu sigma over root n squared. You can prefer either one, but I like writing this one below because at a glance I can see what the standard deviation is, which can be handy for some other questions. Because you have to take note that this number here is variance. And if you need standard deviation, you need to remember to square root this. So up to you, whichever one you learn, but I like this one more, so I just like it. I put it there, happy face. Mu sigma square over n, that's what I've mentioned. This is for the average of a sample. In this question, you've got like the average mass, the average mass of food that they eat. Because it's an average, we use the formula. You've got here was our value that we're using. 3 was our mean expectation. And here we have the standard deviation is 2. The root n is over here, but what's on the denominator is sigma over root n. So when you have probability of some number, in this case it was, that's right, 100 in this case, being 3.5. This is tragic. Imagine people giving a 3.5 for pineapples on pizza. Unbelievable. It would be S100 minus mu over sigma. This is what we covered earlier. Earlier our formula was x minus mu over sigma, whatever the standard deviation of x was. Now we're doing x minus mu of S100 over the standard deviation of S100. I'll write the next part soon, but take note that S100 follows this distribution now. You've got an n to worry about, so that will end up being S100. The mu is the same, fortunately, so just write mu. Now what is the standard deviation of S100? It is the square root of the variance, which is sigma over root n. Oops. And in the slides, she tends to put the root n on top, so that just ends up being root n over here. S100 minus mu over sigma. That's why you'll see the root n just kind of sits here. This is why, because it's division by root n, you put it on top, it's equivalent to the same thing. Now, we did that for our variable, now for the 3.5. 3.5 minus whatever mu, and we want the standard deviation of S100, which is 3.5. I don't have a specific mu right now, I'm just going to put mu, sigma over root n. Please remember that this is the denominator now. But at this point in time, you should get numbers in your question, so you can just sort them in and calculate the probability with a z-table and the phi values. So that was the average. S is for average right now. One thing that the CRT can verify by like extension is that it works for averages, that's what we mentioned, but it also works for sums. So if X followed a normal distribution with mean mu and variance sigma squared, I'm just, what should I, okay, M I guess. M, which is the sums, that's x1 plus x2 plus x3 plus all the way to xn. If this was M, M would follow a normal distribution with mean n times mu and standard deviation n times sigma squared. That's what this slide is saying. This part here. In this case, they use Z. Z is the sum. This is approximately normally distributed with mean n times mu and variance n times sigma squared. So we've got two formulas right now. For sums, this is the formula. For averages, for means, averages. This is the other formula. So earlier I mentioned like this formula equals to whatever on top and whatever on the bottom. That was the star bang bang of the first half of the trimester. I'd say the star bang bang equivalent of the second half, at least for CLT, would be this formula in the box right now, and this formula in this box right now. The first one was for averages, for means. The second is for the sample sum. It's very important to distinguish that difference. So when you do the question, look out for the keywords mean, average, sum, and use the corresponding formulas. There's two of them, so just make sure. Okay, I think that's it for CLT. Next topic is likelihood parameter estimation. That's always fun. Right, so parameter estimation, this comes, oops, okay, where is my whiteboard? Parameter estimation comes about because, let's say, going back to the pineapple on pizza example, there's probably a certain score that they will give, like people will tend to give, or what the actual score would be, but I wouldn't know it ahead of time. Of course I wouldn't. I wouldn't have time to measure every single person and ask them, do you like pineapples on pizza? Or to ask them to rate pineapples on pizza from a scale of 0 to 10. It wouldn't be feasible. So I would never know the true value. Let's make it a discrete variable in this case. I would never know the true variable of whether the value given by a person is more than 5, whether they like or dislike. So let P be the probability that the pineapple on pizza score, I can't write score properly. Oops. Is between 5 and 10. Oops. Between 5 and 10. So this way we have a discrete variable. And it could be like 50% of the population actually does agree. Or maybe just Singapore hates pineapple on pizza and it's very hard to find someone that rates it this high. Maybe it's like 0.3 or it could be 0.7. I don't know the true value that the population has. But there's a certain likelihood that we can narrow it down basically and figure out that, oh, okay, we're reasonably confident that this is what the value would actually be. So what these questions end up boiling down to is that you've got some function, usually called L for likelihood, and it takes in some parameter. Sometimes it's P, sometimes it's lambda. It could be anything really. So let's just use P. And let's say you've taken a measurement. I've asked my 100 people rate pineapple on pizza from a score from 0 to 10. And like out of 100 people, let's say 22 people give a score between 5 and 10. Singapore hates pineapple on pizza, I guess, with that score. So we want to find out the probability that we've measured that 22 people gave that score. So from our sample measurement, we know that 22 people gave that score. So there must be some probability that it exists. And we want to find out what the P would be in order for that to happen. But at this point, you can probably tell I'm using the same numbers as the question in the slides, so I'll just work with that. So in this case, it's a binomial distribution with the slides. So there was 100 people sampled. only 22 of them chose the answer to be like between 5 and 10, and that has some probability p. 22 people chose it. Everyone else, 100 minus 22, did not choose it. So this is a function of p that tells you that shows you data you just measured here, 22. This is how you create a likelihood function. You've got some sample and a certain number of things happened. So let's say you're measuring some variable y. Y is an event that can happen a certain number of times, and you've measured it, and y happens 3 times. So there's some probability of y happened 3 times. This is your probability function. Technically, it's like this, I guess, but they end up being the same thing anyway, so I just kind of like this anyway. This is how you create a this is how you create a likelihood function. Get the number of times something happened, and find the probability of it. In the tutorial, you've got that like network disconnecting question, where it disconnected like 4, then 2, then 7 times. And that was the data that you measured. So you would have 4, and then y equals to 2, and then y equals to 7. Because it happened 4 times, then 2 times, and then 7 times. That's what you measured, that's what you observed, and they all happened back to back, independent of each other. That's why for that question in the tutorial, you had to multiply all these things. Because you observed 3 things when doing your experiment. Yeah, so summary again, when you're creating the likelihood function, you're given data. The likelihood function is the probability of that data occurring. Now that you've gotten your likelihood function, it is a function in terms of p. We would like our event to happen more than not. No, wait, no, let me phrase that. We want to find out the maximum value of p for which this observation that we saw would happen. And that involves finding the maximum value of this function. And how do you find the maximum value? This goes back to calculus. This is where you have a function, differentiate it to find the critical points, and then from the critical points you sub them in and check which one is actually the maximum. That's precisely what we're doing here. So we have this function L of p. In this case we've got, what's 100 choose 22? 100 choose 22. Okay, that's a very big number. I'm not going to write it. 100 choose 22. We succeeded 22 times and we failed the other 100 minus 22, 78. We failed the other 78 times. This is our likelihood function. We want to maximize the likelihood, so we need to find the maximum value. And to find the maximum value, we need to differentiate it. So differentiation of this would be, here you've got 3 things. This is a constant, so I'm not really counting it. You've got this variable and you've got this variable. If you have 2 variables multiplied together and you need to differentiate it, you need to use chain rule. So as a reminder, if you've got square times triangle, they take turns to be differentiated. So you differentiate square first, square prime times triangle, plus, now triangle gets differentiated. Differentiate square first, keep triangle the same, plus, keep square the same, and differentiate triangle. So our constant will still stay the same, you can just keep it on the outside. Now let's differentiate this one. This will be 22p21, and keep the other stays the same, 1 minus p78 plus, keep p22 the same, 78, 1 minus p, bring power down, minus 1, so 77. Differentiate the inside, because that's what chain rule is about, minus 1. And this becomes some giant thing. But the key idea is that at critical points, this whole expression is 0. So when L prime P equals to 0, this entire chunk is equal to 0, and you can solve and you can find a value for P most of the time. It tends to be a value between 0 and 1 if P is a probability. And if it's the case, if they ask you for critical points, they will usually, there we go. Oh, then one of the following is true. Okay. So if you're unable to find the critical points, so there's no solution for f prime x equals to 0, that means that the critical point, or the point with the highest value, is an endpoint, either 0 or 1, or if it's some other parameter, it's minimum or it's maximum. But if there is a critical point, then chances are it's probably that. Just sub these numbers back to your original L function and see which one gives you the largest value. That's how you obtain p hat. Yeah, p hat is just the number that gave you the largest L value. Here we had 0, we had 1, both of us gave us 0. But this number, which is calculated like so, gave us this. Oops. Yeah. Yeah, so the main idea is create the function of L, which is something, differentiate it to find the critical points, and p hat, the maximum likelihood estimator, is the value that gave you the best number, the value that gave you the highest value of L, maximum likelihood estimator. And that's all for that. Now comes the final thing in the topics list, confidence intervals. I have it here as a disclaimer. I am not confident in confidence intervals. I am not sure if what I'm going to say is correct or not. So please understand that, because I have no clue what I'm saying. Okay, not no clue, but I've tried to understand, but not to 100%. Although I was looking at some YouTube videos earlier that seemed to make more sense of it to me, but I'll just share with you what I would do if I faced a question like this in the exam. So we've got, in the tutorial question, they want you to find the maximum likelihood, the lowest, they want you to find PL and PH. Like your lowest p-value that would work with the data and your highest p-value that would still work with the data. And what this ends up being is that, and the great part is that this is in the formula sheet. This thing over here, confidence interval. If you're given a 95% confidence interval, alpha is 0.95. Then to calculate PL and PH, you just sub this in. And that's how you get that. Yeah, that's how you would get this. So it's what I plan to do for this. It's not the most scientific, understandingest approach, but I will take this. I will just evaluate them both. If they ask for PL, I'll just sub it into both formulas and find the smaller number. If they want pH, I'll sub it into both and find the highest number. It's a little bit dumb, but that's what I'm going to do at least. But I'll still go through this question here. We've got this, which was, what we observed was, oh, where's my pen? Okay, our observed data was this. We observed and we counted 22. So there'll be some probability that it will be so low that it wouldn't make sense to have this number 22 anymore. Or the probability was so high that 22 wouldn't make sense to be in there anymore. So let's say, back to the pineapple on pizza example, if the probability of someone saying that the score was between 5 and 10, let's say the probability was 90%. People in Singapore love pineapple on pizza. If that was the case, it'd be super duper unlikely that only like a fifth of the people you interviewed said that, yeah, I like pineapple on pizza. It wouldn't make sense because the probability is so freaking high. And likewise, if the probability was like 0.01, only 1 in 100 people like pizza apparently, or pineapple on pizza apparently, you'd be very hard pressed to find a sample where 22 people said that they would have liked it. It'd be very weird. So what you're trying to find is, what is the probability such that it would make a decent amount of sense. Let me put this here. It would make sense that your reading would be sensible, I guess. Yeah. So this is your reading, and going by the formula sheet, to get PL, it would be x more than equal to 22, given that you're now using PL. And if we have a 95% confidence interval, it's 1 minus alpha. Alpha is 95%, which is 0.95. This evaluates to 0.025. Okay. Yeah, so once you have this, now you need to think about how to calculate this. In the lecture example, there's like 100 different participants. The sample size is 100. So what you would need to do is something like just calculate all of them. Where it's 100, choose x, and PL x. 1 minus PL. 100 minus x. That x is like a number. 0.025. And then she uses some magic calculator to calculate this. We don't have a magic calculator. So when/if this question comes out, I'm pretty sure it will be a lot more manageable. The questions will probably have smaller numbers with them. Yeah, smaller numbers. And that will allow us to like calculate it better. That's kind of it, honestly. I don't have much else to say about this other than, personally, I'm just going to evaluate this guy, top guy and the bottom guy, and if they ask for the lower one, I'll just give them the lower one. Because in the tutorial question, it was flipped. Why? I'm still not 100% sure, and I apologize for that. But with that, since hypothesis testing isn't tested, that's time. 2 hours, 30 minutes, and 21 seconds of math. of math. I've mentioned the formula, I've mentioned the reverse psychology, it doesn't make sense. The third question is different. From what I understand, it's because it's geometric, so things don't quite make sense. It's a whole reverse psychology thing, as mentioned in chat. But yeah, thank you everyone for coming. I appreciate it, and I hope this finds you well. I hope it's able to help somehow. And manage to clarify stuff to you. Oh, so there was a max number. Oh, okay. Watch on Twitch, yeah, pretty much. Link for Twitch, please. I believe it's in my profile. I think it's there. It might be there. I don't know. But I mean, it's no point saying now about Mr. LuGB. That's my Twitch. Thank you for sending that. I actually don't know what your name is. Oh, Mary? No, that's not Mary. It's Mary Juana. Nice. But yeah, thank you for sending the Twitch link. I really appreciate it. If it works, it works. That's really it. If it works, it works. Speedrun, I don't think speedrun.com will accept my timing, but I'll see. I'll try. It's been great. I looked at a bunch of unknowns. I'm glad I managed to help you. Hope, yeah, it's good stuff. And I finished before midnight? Yeah, I finished before midnight. Let's go. Other than like the 1 a.m. from like 2 years ago. Good grief. Yeah. Actually, do I know everyone's profile pictures? I know who you are. I know who you are. I think I know who you are. I have no clue who you are. No clue. Not sure. I know. I think I know. I know. I think I know. I know. Not that sure. I've seen this one before for a very long time. I'm not sure who that is. I'm not sure who this is. I know who this guy is. I know who this guy is. I'm not sure who that is. I know who you are. 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 I am not sure who you are. I don't know who you are. I know who you are. Pretty sure I know who you are. No, I know who you are. Yeah, I know you. I know you. I'm not that sure. I know you. I think I know you. I know you. Do not. No, I know you. 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 Yeah, I know you. I know you. Brilliant nickname. I know you. I know you. Yeah. Okay. Oh, what was the whiteboard? If anyone did write anything there, because I didn't want to use the whiteboard because it was a. It's. I tried using it previously. It wasn't that great. It's brilliant. I love it. I love what you guys have done with the place. How do I pan? Oh, middle click. One more day, exactly. It's just like 12 hours from now. No, maybe not 12. It's like 16 hours from now. All of our exams will be done. So that's there to look forward to. So that's fantastic. Uh, oh, wait, I don't. Can someone get like a plaster for this poor man? I don't know who this character is, but they're great. I'll just stick around maybe till like 12 or 1. I might do tutorial questions. I'm gonna have a water break first, maybe a toilet break, then I'll come back. But I'll probably still hang around. Um, yeah. Did I stop the stream? Yeah, okay, I can stop the stream. Alright, goodbye Twitch. I'm not. Hey, should I still stream if I'm doing tutorial? Nah, I'll keep it going. It's fine. So, anything else for me to do? No, that's right. Yeah. Oh, thank you for sending the Twitch link. I really appreciate that. Um, yeah, okay. I'm just gonna write break time, I guess. I'm just gonna like be back soon. I don't know when I'll be done. Okay. Oh, no, I did it! Oh, let's go! Butter potato. Alright, humans, I have returned. Oh yay, someone put the plaster on Luigi, thank you. Right. As for what to do, I feel like there's only one main mystery left, and that's that one tutorial question. Oops. Thing. Open a new window. Here we have tutorial 11 and the tutorial 11 solution. And we've got the whiteboard. Because question 3 is the question of this tutorial. And I'm almost certain about that. But yeah, I'm gonna just attempt to make sense of this question, but if you guys want me to just talk about the other questions, feel free to just mention them now. I don't think there's nearly as many people in the call, right? No, there's still a lot of people. But yeah, if you want to ask a specific question, I can just go through it quickly, I guess. But if not, I will just try to focus on this. Or at least try to make sense of it. Oh, I should have the slides open too. Actually, I didn't know that Discord had a maximum number of people in the call. It's pretty surprising. I figured you could have like a whole bunch of people, but I guess not. Although I don't know whether the quality is better on Discord or better on Twitch. I really have no clue. I'm just glad my computer didn't crash at all during this entire process, because previously when I tried to like extend my monitors between different screens, it used to crash a lot. So that's fortunate, I guess. The upper limit and the lower limit of Q. The probability is Q. So this is our line of probability. Oh wait, I can hold the line. Yeah. This is 0 and this is 1. Q could be anywhere. Store it here. If P, if Q, there is a, I hate how this question has PH and PL, but the variable is Q. That's just inconsistent. But oh well. Find the upper limit of the 95% confidence interval for Q. If the probability, I'm trying to find P or Q. God damn it, I'm trying to find Q. Find the upper limit that, oh wait a minute, does that make sense? P, no, Q, god damn it, this Q, the probability that you still get x equals to 2 given that you have the upper limit. This is of course 0.025. But when the probability gets higher, you would expect it to win. When the probability is high, if probability was 0.999, getting x equals to 2 would be hilariously unlucky. So it would only make sense that with a high probability, x would be lower. Hold up. Oh, wait a minute. I think I'm getting to make sense of this. I think so. Okay, for whoever who's listening, I don't know how many people or if there are people listening right now, but I think I have an idea why this question uses the formula the way it does. Okay, let's just write it out formally. So we have some variable, oops. X is the number of times needed to win the lottery until you win. That's a geometric distribution with the probability Q. And we observed, that it took 2 wins for that to happen. Now our objective is to find, I'm just going to call it QH, PH is stupid. I'm trying to find QH. Logically, if Q increases, because QH is the upper bound, the number of trials needed to win the lottery would decrease, because if your odds of winning are super duper high, chances are you would win in like the first time you play. But we want to be confident that you would win in the first like region, in the first term. So we would be confident. What an oxymoron. I'm saying the word confidence so unconfidently. I think that means, okay, therefore, it would be very unlikely to have a large number of attempts, and that is attempts. That is what X is. So the probability of X being large should be tiny. It wouldn't make sense to have a gigantic X value if the probability of winning was super freaking high. So that means, okay, the confidence interval is 95%. So this must mean that we are 95% sure that X is a small number, because it would take like 1 or maybe even 2 tries to win if the probability was really high. So the probability of X being large should be tiny. I think that's the most important statement here. because of that, I think I got it, but I'm really not sure. Okay, let me read through my logic again. We have a random variable that is geometrically distributed with a probability q. We have one sample where a person wins the lottery the second time he plays. That means x was equal to 2. That's what we observed. So we're trying to find the upper limit of this confidence interval. Upper limit means Q is big. If Q is big, the number of trials needed to win the lottery will decrease, because if your Q is gigantic, the probability of success of winning the lottery will be really high. You wouldn't need that many trials to do it, to win. It will be very unlikely to have a large number of attempts. So we are confident that it takes a small number of attempts. So the thing that lies outside of our confidence interval is what we are not confident in, I think. This means... what does it mean? What does it mean? What does anything mean? This means you will be unlikely to have a large number of attempts, which is x. X is the number of attempts. Probability being large should be tiny in this case. Can this logic still work with the lecture questions? Because if it does, things might start making sense. Thanks, man. I really appreciate it. By the way, anyway, the foods you had for dinner were, was it the dragon fruit and the fruits? Oh, okay. I think I'll have it tomorrow. Thanks, man. Okay. I think I may have finally understood confidence intervals. Keyword being think, because I really don't know. But this approach that I seem to have cooked up kind of works. Not kind of works. It gave me the right formula to use for both tutorial question and the lecture questions. So I'll just run through it with you all, I guess. So for the tutorial, okay, for the tutorial we have the following. We have x, which is some geometrically distributed variable with the probability q. Then it says we have one sample, so we have yet one observation that this one random person won the lottery the second time that they played. So we observed that x was 2. And our objective is that we want to find QH. I'm going to write QH and not PH. I want to find QH, the high value of Q, that kind that still allows this to happen. So QH is high. It's higher than what Q probably is. So as Q increases, it gets closer and closer to QH. The probability of winning increases. So probability of winning lottery increases. And because the probability of winning the lottery increases, this means that you would expect to win sooner. So expect to win sooner. And because you expect to win sooner, the value of the number of attempts, which is x, should decrease. Because if your probability of success was so high, you would win pretty fast. It wouldn't make sense to have x be 100 if the probability of winning was like 0.9999999. You would win super quickly. So if the number of attempts should be decreased, that's what we would expect. But this is about confidence intervals. So we would be confident that x would decrease. By extension, we would not be confident that x would increase. Because the probability is so high, x should go down. But if x increases, we're like, wait, what the heck? That doesn't make sense. So we're not confident that that should happen. And because we're not confident, this event that x increases should lie outside our confidence interval. This means that the probability of x increasing past our original observed value, which is 2, this is outside the confidence interval. And since our confidence interval is like that, with 0 and 1, maybe our Q is like here. QH is like this way, and QL is probably like here. So as our probability is increasing here, you would expect X to decrease. But it's increasing, which doesn't make sense. So
Sorry to interrupt, but I think
Yeah,
the
go
Q
ahead.
should be the center of this. QL and QH should be equidistant from Q.
Oh, is that guaranteed?
Yeah, it guaranteed. If you look
Oh.
at her formula, she can't divide by 2.
This division by 2?
Yeah. So I'm not exactly sure how she does it, but the way I look at it, it's more like the confidence interval starts from Q and kind of spreads out in both directions. If you get what I mean. So the range of 95 is encompassing from Q and spreading out in both directions to form 95. If you were to use a formula, it uses so alpha in this situation is a decimal conversion of percentage.
Yeah.
So if you do 1 minus 0.95 divided by 2, you get 0.25. 0.025. Yeah. So you can kind of see that that's the end point, which is the lower. If you do the upper, it will be the opposite way around. You do 1 minus that. And if you minus the upper and the lower, you find that the confidence is exactly what we're looking for, which is 95.
Can you repeat that last part again?
So for the lower,
Mm-hmm.
it's you just take the value. Upper, do 1 minus the number that you just got. That will get your upper. So what you notice is that when you use the upper minus the lower limit, you will get your confidence level back.
Okay. Oh, okay,
Yeah.
okay.
So that's how I think it's supposed to work. She never really explained that part clearly.
Yeah, she not quite. I mean, she even said in the recorded lecture that this is the confusing part.
But yes, the confidence level should be
Equidistant, right?
yes.
Okay, let me amend that. Where's my pen? I think this is the kind of logic I'm just gonna use in the exam. The whole writing words thing. I think it'll help. I hope it does. I think maybe I'll stick around until 12:45. Then I'll probably head off then. But in the meantime, I'll just hang around. I remember saying at the end of my previous speedrun that I wish I had splits. So that's what I did this time. You can even see which parts I took more time than others. This was super fast. Conditional took quite a while. Oh, I have a... What's the 8.29. Oh, you can subtract time that way. Took about 4 minutes each for independent, dependent, and conditional probability. Bayes' theorem was like pretty big. 33, 48. That was like half an hour for Bayes' theorem. For 25 minutes. Like, we have 40, 40. It's like 6 minutes. For PNC, inclusion, exclusion took about 7 minutes. Discrete and continuous took forever. CRT took a while. Parameter estimation took a while. Confidence interval took a while too. Actually, I think I don't really have much else to like say. So unless you guys have any questions I can try to answer, I'll probably be heading off now. Oh, I didn't see stuff in the chat. I'm not sure who Kamitaka is, but am I gonna upload the VOD? Absolutely. Right after this, actually. So, and then the other thing was silver or silver. Yeah, okay, the equidistant part doesn't matter. Interesting. And then you say that still don't make sense if less number of x still should be x less than beta given p of h. Yes? I don't know. Man, how do you care? Yeah. Just follow the slides. I'm just going to evaluate both. Tutorial answer, it's because it's geometric. That's the thing that messes up that specific question. Oh yeah, and don't worry, I will be sitting in front tomorrow. Yes, I'll be right in the projector. Don't worry, GCWW. But yeah, the proper answer, it's because it's geometric. It's just what's that emoji for this one? Okay. But yeah, if there's nothing else, all the best for tomorrow. What's the clapping emoji? There it is. See you. No problem then. No worries. All the best.